Let me to say something about domatic partition and domatic number that I had this presentation about 2 weeks ago. And you know domination number, and Alexandra introduced the domination number. A set is a dominating set if every vertex which is not in the set D is adjacent to at least one vertex in D. And you know domination number is the minimum cardinality of dominating set in G. As an example, you see in this figure the black vertices, which are 1, 8, and 10, is a dominating set of this graph, and this is a minimum cardinality of a dominating set of graphs, and so the gamma of this graph is 3. And all of you know the domination number has many applications, such as communication network, radio station, and social network theory. And as Alexandra says, we have many another dominating set in graphs. Maybe the second important one is total domination number. And you know the total dominating set is a subset D of V, such that every vertex in V is adjacent to some vertex in D. And the total domination number denoted by gamma sub T and is the minimum size of total dominating set. As you see here, we have a Petersen graph, and the left one shows the red vertices shows the dominating set. So the gamma of Petersen I mean,
Saeid, what happened, Saeid?
Yes, we here we do not have a good internet. Sorry, it's better to disconnect my webcam. Okay, and again, do you hear me, Hamid?
Yes, yes, I can.
Okay, sorry. Okay, you see here an example of the domination number for Petersen graph and total domination number. As you see, the gamma t is greater than or equal to gamma. And all of you know, I am sure that know these three good books, and everyone that want to research in this area should be have these three books. And let me to introduce and recall another kind of dominating set, which called S-string dominating set. A set D is a S-string dominating set if every vertex which is not in D, for every vertex X which is not in D, there exists a vertex Y in D which is adjacent to X, and degree of Y is greater than or equal degree of X. And the S-string domination number denoted by gamma sub ST and is the minimum number of S-string dominating set of G. And obviously a gamma ST set is a S-string dominating set of minimum cardinality. And if the S-string dominating set, we say a vertex U is strongly by V if UV in E of G and degree of V is greater than or equal to degree of V. And similar to S-string, we can have the definition of weak dominating set, and the minimum cardinality of weak dominating set is denoted by gamma sub omega or gamma sub W. You see here a graph, 4 black vertices are dominating set of this graph, but these four vertices in the middle of this edge are not a strong dominating set. So we have many dominating set in graph which are not strong. And you see here another example that shows that maybe the strong dominating set of a graph is less than weak domination number, and also and vice versa. A strong domination number maybe is greater than weak domination number. So, okay, let me to say about the Domatic number. Domatic number introduced by Cocaine and Hedetnami in 1977. And what is a Domatic? A Domatic partition is a partition of the vertex set into dominating sets. In other words, we have a partition pi, v1, v2, and vk of vg such that every vertex vi is a dominating set in G. And domatic number denoted by d of G and is the maximum order of k in this partition. Okay, so domatic number of a graph denoted by d of G and is the maximum order of sets in the partition of vertex set into dominating set of a graph. For example, here you see in the left we have a cycle with 5 vertices, and you see the vertex set of C5 has partition 1 and 3, which is dominating set 1 and 3, and 2, 4, and 5. So here you see the maximum number of partition of vertices graph to dominating set is 2. Okay, so domatic number of C5 is 2. And in the right figure, we have a cycle C6, and you see a partition of vertex set of C6 to 1 and 4, the 2 and 5, and 3 and 6. Obviously, 1 and 4 is a dominating set. Also, 2 and 5 is dominating set, and 3 and 6 is a dominating set. So, domatic number of C6 is 3. Domatic number is 1 if G has at least one isolated vertex, and so what happened to graphs? This is a very good and interesting problem, that what kind of graph have domatic number 2 and 3 and so on. Here you see a theorem by Jigger and Poyant that say if G has a diameter less than or equal to 2 and every edge of G is in a triangle, then the domatic number is at least 3. For example, you see here a graph, very simple graph with four vertices that diameter has 2, and every edge in this figure lie in the triangle, and you see domatic number is 3 because we could to partition the vertex set of this graph to 1, 3, and 2 and 4. Note that this theorem by Jigger and Poyant is not a necessary condition. For example, you can consider C6. And you see some upper bound and lower bound for domatic number of graph. You see an upper bound by delta plus 1 and lower bound by floor of n over n minus delta. And for total domatic number, we can have this lower bound, and the second theorem says if G is a finite graph with n vertices for n greater than or equal 9 and delta equal to n minus 3, then total domatic number is exactly half of n. Okay, so obviously for any kind of dominating set, we can have domatic number. Here we introduce a string domatic partition. A partition of V of G, all of whose classes are a string dominating set, is called a string domatic partition, and the maximum number of classes of a string domatic partition is called a string domatic number, and we denote this parameter by d sub st. For example, in this graph, you'll see the string the string domatic number is 3 because we can partition the vertices of this C10 to 3 subset. The first subset is the vertices with labels 2, 6, and 8. Another one is vertices with 1, 3, and 9, and the last one is 4, 5, 7, and 10. Obviously, all of these vertices are a string dominating set, and we could partition the vertex of this C10 to 3 subsets. So a string dominating set of this graph is 3. We have this theorem that says if a graph has a pendant vertex, means that if a graph has a vertex with degree 1, then a string dominating set of graph is 1 or 2. And obviously for any regular graph, we have a string domatic number is equal to domatic number of G, and a string domatic number is less than or equal k plus 1, where k is the degree of vertex of G, vertices of G. And here you see another lower bound and upper bound for a string domatic number. G is a graph with maximum degree capital delta, and M is the number of vertices with degree capital delta. Then the string domatic number is between 1 and M. And these bounds are tight. For the lower bound, it's sufficient to consider the star graph K and 1. Obviously, for a star graph, the string domatic number of a star graph are 1. And for the upper one, obviously, we can consider the complete graph. And here you see some result for computation of a string domatic number of some specific graph, such as path cycle, bipartite graph, and friendship graph, and book graph. You see the string domatic number of paths is 2, and for cycle we have 3. The string domatic is 3 for n equal to 3k, and otherwise we have 2. And for bipartite graph, you see if if n be less than m, then the strength domatic is 1, and if we have the same number of vertices in parts, then the strength domatic number is the number of vertices in one part. And for the friendship graph, that friendship is the join of some triangle in one vertex. In other words, a friendship graph is the join of k1, one vertex k1 with n k2. And obviously the strong domatic number of this graph is 1. And for book graphs, the strong domatic number is 2. And here you see a result about a strong domatic number of Koronov graphs that I denoted by circ. A strong domatic number of G circ H is between 1 and a strong domatic number of G. And the second one says that domatic number and a strong domatic number of Petersen graph are unique among the cubic graphs over the time. It means that the Petersen graph can determine by domatic number, its domatic number and its strong domatic number in between all cubic graphs over the 10. Okay, here let me consider the number of domatic partition in a graph. And we are interested to count the number of domatic partition, which is not, I think, easy problem. Let dpgi be the family of domatic partition of a graph with cardinality I, and the cardinality of this family denoted by dpg on I. And let me to call this sigma dpgi x to the I a polynomial, which is a domatic polynomial. I am not very satisfied with this name. It's better to, but let me here call this summation as a polynomial. I consider it as a domatic polynomial. So here the coefficient of x to the I is the number of domatic partition of a graph with cardinality I. Obviously here I is from 1 to domatic number, okay? And since domatic number is always less than or equal delta plus 1, then we can have this summation as a summation from I1 to delta plus 1. Okay, let me to give an example here. If we have a pass P2, then obviously we have this polynomial x plus x2 because the number of the number of domatic partition with cardinality 1 is 1, and with cardinality 2 is also 1. And again, we have the same situation for P3. The domatic polynomial of P3 is x plus x2. But if we consider here past P4, as you see in this figure, we have two cases, and the number of partition with cardinality 1 is 1, and we have two uh, two partitions with cardinality 2. And for P5, the domatic polynomial is x plus 3x2. Here we have three cases for the number of partition of the vertex set to domatic partition. Okay, we know that the computation of domatic number is NP-complete, so the computation of these domatic polynomials is NP-complete, means that um the number of partition uh, is NP-complete. And you see here are some properties of this polynomial that says if G is a graph and domatic number is R, then domatic polynomial at 1 is 1, and domatic partition at 2 is the number of weak 2 coloring that I say more about it in the next slide. And DPG and 1 is the number of all domatic partition. And if we have some another properties for air derivative of this polynomial. And obviously 0 is a root of this polynomial with multiplicity 1. And no, what is a weak K coloring of a graph? Since we are interested to the number of partition, this number has a relationship between this partition and the K coloring, weak coloring of a graph. A weak K coloring of a graph assign a color C of V to every vertex V, such that each non-isolated vertex is adjacent to at least one vertex with different color. For example, in this following figure, this coloring with two color white and black is a weak two coloring. Is weak two coloring because every vertex, for example, with black color has at least one vertex with different color, which is adjacent. So this coloring is too weak coloring. Note that this coloring is not proper because, for example, these two vertex have the same color. Okay, we have this note that if there is no isolated vertex in the graph, then a weak two coloring determines a domatic partition. The set of vertices with color black is a dominating set. For example, in this figure, the vertices of with black colors are dominating set, and the set with another color, white color, are also are dominating set. So, and this weak two coloring is equivalent to finding a domatic partition of a graph of size 2. And so we have this definition that if capital omega of G and 2 be the family of weak 2 coloring of the graph, and the number of this family is denoted by omega sub 2, then dPAGN2 is exactly omega sub 2 of G. Means that the number of partition, domatic partition of size 2 in any graph is exactly the weak 2 coloring number of G. And so we have this theorem that if T is a tree, then domatic number of tree is 2, and domatic partition of this tree is x plus omega sub 2 x to the 2. So we have this simple result for domatic polynomial of any tree. You see here domatic partition, domatic number of any tree is 2, and the number of domatic partition with cardinality 1 is 1, and the number of domatic partition with cardinality 2 is omega sub 2, which is 2 coloring, 2 weak coloring graph. Okay, let me to say another definition here. Suppose that we have a tree T and U is a support vertex. Let ones of U be the collection of vertices that have a degree 1 and share an edge with U. So ones of U is a collection of vertices that have degree 1 and share edge with U. And let T sub U to the minus 1 and T sub U to the minus 2 be two trees obtained from T by removing vertices 1 of the U and ones of U with U itself. Okay, so we have these two notation here, T sub U to the minus 1 and T sub U to the minus 2. And in a tree, we call a vertex V as a quasi-star vertex of tree if satisfied the following condition. The first one says the vertex V should be adjacent to exactly one non-leaf vertex, and the second one says V is adjacent to at least one leaf. And any tree that contains a quasi-star vertex, we call it a star neighbor tree. For example, here you see a tree that the vertex V is a quasi-star vertex. And here we have a theorem about weak 2 coloring number of tree for any, that's here, this theorem says that for any star neighbor tree T of order n, at least 4, if Y is its quasi-star vertex, then we have this formula for to recoloring. Omega sub 2 of T is equal to omega sub 2 T sub Y to the minus 1 plus omega sub 2 T sub Y to the minus 2. And by this theorem, we can have this corollary that says for any path Pn of order n at least 4, omega 2 of Pn is equal to omega sub 2 of Pn minus 1 plus omega sub 2 Pn minus 2, where omega sub 2 of P3 and P2 are 1. And obviously, by this recursive formula, we have this Fibonacci sequence, and we see Fibonacci numbers, and the golden ratio appears in this topic as this corollary. For every n at least 4, the domatic partition of pass with cardinality 2 is exactly the Fibonacci number. So we have this result that says the number of domatic partition of pass with cardinality 2 is exactly the Fibonacci number. And so we can have this corollary that says if we compute the limit of omega 2 of Pn plus 1 over omega sub 2 of Pn, because of Fibonacci properties, this limit would be the phi, where phi is this number, 1 plus a square root of phi over 2 is golden ratio. So golden ratio appears in the this subject. And because I am interested to Fibonacci number in graph theory, and recently I published a survey paper about golden ratio in graph theory. Okay, and here we have another definition that says that suppose W1, W2, and Wk be some vertices of a graph, and B, G, semicolon, W and Wk be the banquet of a graph with respect to the vertices Wi and obtained by identifying the vertex Wi of the graph with vertex W. And by this definition, let me to introduce two kind of tree that I denoted by T and T prime. Consider a tree denoted by T and select a support vertex in this tree labeled Y, and suppose that the neighborhood of Y minus the ones of U be W1, W2, and Wk. The theory obtained by banqueting the vertices W1, W2, and Wk in W, denoted by T prime in the right figure. So from this tree, the left one, and the banqueting operation, we can obtain another tree, which is denoted by T prime. And we have another theorem about the two-week coloring number of tree that says that for any tree T of order at least n, if Y is one of its support vertices, then omega sub 2 of T is equal to omega sub 2 of Ty to the minus 1 plus omega sub 2 of T prime sub Y to the minus 2. And here you see another result for domatic domatic polynomial of Pn corona with K1. As you see, the number of domatic partition of this kind of graph with cardinality 1 is 1, and the domatic partition number of this graph with cardinality 2 is is to the n minus 1. And we have the same result for the graph G corona of G and R isolated vertices. So domatic polynomial of G circ over line KR is x plus to the n minus 1 x2. And you see here an algorithm to compute these two-week coloring of in any tree T, and that is a very simple algorithm. And the input is a tree, output is omega sub 2 of T, and you see another program. And we could, to prove that the worst case time complexity of the algorithm for computing this number, omega sub 2 of T for any tree over the n is O n2. Okay, actually, I presented this lecture in and I prepared for, I think, 30 minutes or 35 minutes, but here let me just say something about the application of domatic number in coalition of graphs, which is a very interesting subject in graph theory. Suggested a graph theoretical model to describe a coalition government whenever in a general election no political party achieves a clear majority, then in such cases, two or more parties form coalition cabinets. Because of this motivation, Hines, Edatnami, and McRae and Mohan introduced a coalition in graphs in 2020, and here I just say about definition and motivation and application of domatic number in this area. Maybe you know the definition of a coalition in graph. Hamid say very well, know very well about this parameter because he works in this parameter very well. A coalition in a graph is a pair of sets S1 and S2 that are not dominating set, but the union is a dominating set of G. So this is a definition of a coalition in a graph. Coalition which is related to dominating set. So a coalition in a graph is a pair of set S1 and S2 that are not dominating set, but their union is a dominating set of graph. And a coalition partition is a vertex partition A1, A2, and AK such that each set AI in this partition is either a dominating set with cardinality 1, or there exists another set AJ in this partition that forms a coalition with AI. And the coalition number C of G is defined as the highest number of sets can be included in a coalition partition, okay? So this is a definition of a coalition partition and coalition number of a graph. And for example, consider P9 in this figure. Obviously, these four first vertices are not dominating set of graph, and also the last three vertices of this P9 is also are not dominating set of this graph, but their union can be a dominating set of this graph. So these two sets are coalition of graph. Or, but obviously this is not the maximum number of partition. Here we show the maximum number of partition of P9, and you see the number of, I think, color that used here is 6. So the coalition number of this graph is 6. Actually, obtaining and computing the coalition number of a graph is not easy, I think. And the first paper in coalition of graphs is about the computation this number for past cycles and specific another graphs, for example, bipartite graph and so on. For example, you see here the coalition number of pass and cycle. I think about 6 pages of this paper of Highness in 2020 is for computing the computation number of pass and cycle. And you see here some bounds for the coalition number and another properties of this coalition number that you see here, that coalition number is 1 if and only if G is a vertex, and coalition number of any graph is 2 if G is a K2 or 2K1 or over ln of K2, and if G is isolated free, and coalition number of graph is 3 if and only if G is a star or K3. And there are some another result on coalition number. Here you see if G is a graph of order n with isolated vertex, then the Hamid, do you hear me?
Yes, Said.
Sorry, I disconnected.
It doesn't matter. Doesn't matter.
Okay, I think I should stop here and finish my presentation. Sorry. Here, when we want to use the Zoom, we should use the VPN, and this is a problem in Iran. Okay.
Through
sorry.
VPN, yes? Okay.
Yeah. Okay. If there is any problem, there is any question or idea about my presentation.
If you have any question, please turn on your mic and ask your question.
Okay.
And Said, I have a question.
Okay.
Okay. There are many types of dominating sets, such as Roman dominating set, total, independent, connected, and so on.
Yeah.
And what is the motivation to explore the new parameters? And this is my main question.
For Domatic, you mean?
No, I mean the dominating sets.
Oh, what is the motivation for introducing many dominating sets in the graph?
No, actually, yes. Actually, what is the main? What is the main motivation
Hamid,
to explore the new parameters?
Yes. Hamid, I think there are more than 70, about 75 kind of dominators in the graphs that introduced before, but I think maybe no all of them are important. In my opinion, maybe 7 or 10, maybe at most 10 of them are important and have very good motivation and application in some another area. But maybe introducing another kind of dominating set is not very good idea, because we are I think sufficient many dominating set. But actually, if any new concept in graph theory has an application or motivation, and maybe or have a interesting properties, then we can consider as a new concept in the graph theory. Maybe the leader of domination theories should answer you. For example, Professor Henning or maybe Edith Navy. Okay. Yeah.
Okay, thank you very much.